And if you were to take a chemical engineering fluid mechanics class, one of the things you're concerned with is what happens when you have a pipe like this one, and you've got, let's say, water or oil or some kind of other fluid flowing through this pipe. Well, the motivating force behind all fluid flows, whether it's a gas or a liquid or whatever, is pressure difference, okay? If you have an area of high pressure and an area of low pressure, then fluids are going to move from high pressure to low pressure. This is just like electrical circuits, right? In an electrical circuit, your current wants to move from high voltage to low voltage. Did I say that right? I'm not an electrical engineer, so I don't know. But for fluids, they move from high pressure to low pressure. So if I go out right now and I find Kevin's car and I take my pin and I jab a hole in his tire, what direction does the fluid move? Does air go from out in the atmosphere into his tire through the pinhole? No. Air flows out of the tire because inside the tire you have 32 psi's of pressure above atmospheric pressure, and the fluid, the air, flows from an area of high pressure to an area of low pressure, so it flows out through the tire. So if the water or the whatever it is flowing through this pipe, it must be because there is higher pressure here and lower pressure here. And so one of the things that chemical engineers are interested in is, what is the pressure drop? In other words, if I take the higher pressure minus the lower pressure, I get a pressure difference, and we call that pressure drop, and we use a little capital Greek delta for the difference in pressure. So we chemical engineers use this formula, and it says the pressure drop is equal to a lowercase f, which is called the Darcy friction factor, times capital L, which is the length of the pipe, divided by d, which is the diameter of the pipe, times 1/2 times rho, and that rho is the density of your fluid, times v squared, where the lowercase v is the linear velocity. If you were to track one of the molecules, what's its average velocity moving through the pipe? That would be your lowercase v. So the very end of this equation might seem familiar to you. This 1/2 rho v squared. 1/2 rho v squared should kind of look like something from physics. You guys have all taken a physics class? What's the kinetic energy of a moving object? Nobody? So the kinetic energy of a moving object is 1/2 mv squared. That's kinetic energy. Kinetic energy is like the antiderivative of momentum, because momentum is mass times velocity, right? Take the antiderivative with respect to velocity and you get 1/2 mv squared. You get kinetic energy. Well, this is not an object. It's not a solid object moving through space, but you have this liquid or this fluid moving through space, and so we use density instead of mass, and we get 1/2 rho v squared for kind of the kinetic energy of this fluid. So the drop in pressure is proportional to the kinetic energy. It's also proportional to the length of the pipe, because the longer the pipe, the more pressure drop we expect to find. It's inversely proportional to the diameter of the pipe, because if you have a large diameter pipe, that makes it easier for fluid to flow. There's less resistance. You know, it's like, have you ever, maybe you do this every day, I don't know. At lunch, do you drink your lemonade through like one of those crazy straws that goes like woo, woo, woo? It takes more effort, ever so slightly more effort to drink lemonade through a crazy straw versus if you go to McDonald's. McDonald's will give you a disposable straw that has like an extra wide diameter because they want you to drink your soda faster, I guess. And it doesn't take as much effort to drink with a McDonald's straw. So that's the effect of the diameter. That's the capital D. The larger the diameter, the lower the pressure drop because there's less resistance. And then the last thing, the lowercase f, is called the friction factor. And the friction factor is a way for chemical engineers to quantify how much friction is happening, number one, between the fluid and the walls of the pipe. So you sort of lose some efficiency because friction happens when the fluid moves past the wall of the pipe. And then also when the fluid moves past itself, because in the fluid there's going to be eddy currents and some turbulence. And so there's going to be internal friction between the fluid and itself. And so that's quantified using the Darcy friction factor. And there's a lovely equation that we use for Darcy friction factor. And it's shown right there in the middle of the screen. It's 1 divided by the square root of f is equal to 1.93 times log base 10 of capital R times the square root of f minus 0.537. Now the capital R is called the Reynolds number. In the calculation of Reynolds number, the numerator has rho, that's our density, times v, that's our linear velocity, the speed it's moving through the pipe. The capital D, that's the diameter of the pipe, and we're all dividing by mu, and that lowercase mu is called the dynamic viscosity. So maple syrup has a high viscosity, but water has a pretty low viscosity. Okay, it's the stickiness of a fluid. And so Reynolds number turns out to be dimensionless. If you cancel out all of the units between the density and the velocity and the diameter and the viscosity, all of the units cancel. So it's what we call a dimensionless number. And this is what we do to calculate Darcy friction factor. So you'll notice in that equation right there in the middle, if we can calculate our Reynolds number, then there's only one Darcy friction factor that's going to make that equation true. Our problem is that that equation gives us the friction factor implicitly. On the left side of the equation, I don't just get F equals, and then on the right side of the equation, some kind of expression that doesn't involve F. That would be an explicit formula. But this is not an explicit formula. I've got F that appears on both the left side and the right side of the equation. So that's a huge pain, and it's not easy to solve analytically. So what are we to do? We are going to take this equation and we are going to define y equals 1 over square root of f. And that means f is going to be equal to 1 over y squared. Double checking to make sure I'm doing the math right. I'm a little tired today. And then I can write this formula, or the equation above, as y equals 1.93 times log base 10 of the Reynolds number divided by y minus 0.537. And for this entire right side of the equation, I'm going to call this g of y. So I can write y equals g of y. And then I'm going to make this into an iterative equation solving technique by doing this. I'm going to say that my next iterate for y is going to be equal to what I get when I solve and evaluate the right-hand side of this equation at my previous iterate. Does that make sense? So now let's, we'll do this, and you could do this with a calculator, right? I hope everybody understands you could do this with your TI-89 calculator. But for, not wasting your time here, I'm going to come up with an initial iterate for y. You just have to make this up. I'm going to choose the number 1. It seems easy. And then the right-hand side of my equation, I think, was like 1.93 times the logarithm base 10 of the Reynolds number. I'm going to have to come up with that here in a second. Divided by y. I don't remember the rest. It was like plus 0.5 or something like that. Let me go back and look. So 1.93 times log base 10 of r divided by y minus 0.537. Okay. And then in cell E2, I need to put my Reynolds number. And my Reynolds number was a function of the density, the velocity, the diameter of the pipe, and the viscosity. And so for water, the density is going to be 100 kilograms per meter cube. It's an SI unit, so it's really easy to remember. For the velocity through my pipe, we're going to say the velocity is 1 meter per second. For the diameter of the pipe, we'll say it's 1/10 of a meter. And for the viscosity of water, let's say 0.00089 Pascal seconds. SI units are nice and easy. And so that means my Reynolds number is going to be density times velocity times diameter divided by viscosity. That's my Reynolds number. And so I've got my right-hand side of my equation. And the idea behind my iteration was that my next guess at the left-hand side of the equation was just going to be equal to the right-hand side, right? And I evaluate the right-hand side. So let me set that equal to the right-hand side. And then I'm going to use the formula for the right-hand side again, using my new guess about the left-hand side. And I see what happens. In my Excel formula here, the E2, I need to lock that cell reference in place. There we go. Now, what do we see? After a few iterations, it gets pretty good, right? It looks like I'm converging onto a number that's like 7.5196-ish. And so if I actually want my Darcy friction factor, I have to do 1 divided by y squared. And my Darcy friction factor is something like this. I've got 5 significant figures of accuracy after like 7 iterations or something like this. So, does everybody understand what I just did? Been very quiet. Do you have any questions? We had this big, ugly, implicit equation that I could use to solve for friction factor. It's not an explicit formula. I don't have like a good function where f is a function of r or anything like that. I've got this nasty equation. And in practice, I guess you could take the right-hand side and subtract the left-hand side and set it equal to 0, and then you could use Newton's method to find the 0 of the function. But then you got to calculate the derivative of that, and that's nasty, and who cares, right? In practice, the way they taught me in chemical engineering school was you do this fixed point iteration. You just plug it in over and over and over and over and over until it gets good enough. But I don't want to move on unless you'll get it Can you nod your head if you feel like you could do this on a test? No? Aaron, what part is confusing? What's getting you right here?
I'll just go back and watch the video.
Okay. All right. So that's the idea. This is called a fixed point iteration, and this is going to be the last thing I say about solving a single variable equation, is that like we have learned in this class now how to do bisection method and secant method and Newton's method and all of those other things. Plus, you can also just use a fixed point iteration if you happen to know some kind of implicit relation like this. The technical definition of fixed point iteration is an iterative scheme of this form where you generate a new iterate by evaluating a function of your previous iterate. We hope that this is eventually going to converge to a point where it's a fixed point. And a fixed point just means if I plug the fixed point into my iteration function, then it's going to spit out the fixed point again, right? I can keep doing that over and over and it's going to be exactly the same. That's our goal. And so this point is called a fixed point. And what we just did with the Darcy friction factor would be considered a fixed point iteration. Here's a question for you guys. What is one other fixed point iteration we have already learned about this semester? What else fits that description exactly?
Bisection.
No. I'll tell you, bisection method does not fit the definition of a fixed point iteration because the bisection method calculates your next iterate based on the previous two iterates, right? Like it's based on a lower bound and an upper bound, not just based on the previous iterate. Newton's method. Yep, so we have learned about Newton's method, and Newton's method is technically a fixed point iteration. In Newton's method, we say something similar to this. Which looks just like a fixed point iteration, where this capital N function is called the Newton map. But yeah, technically that makes any Newton's method iteration into one of these fixed point iterations. But I wouldn't say the bisection method is, because like I said, it relies on like a lower bound and an upper bound that get updated, not just the previous iterate. Same thing for secant method. Secant method technically doesn't fit the bill because it requires the previous two iterations to do the secant method. So really the Newton method is the only other fixed point iteration we've learned about. But this is the strict, rigorous definition of fixed point iteration. The mean value theorem assumes you've got a function f, and it's continuous on some closed interval, and on the same interval it's differentiable. So just assume it's a well-behaved function. Then there should exist at least one point inside that interval where the instantaneous rate of change is equal to the average rate of change from A to B. So this formula is kind of the rigorous way of stating that, where the point C is in between A and B. Another kind of less formal way of saying this is if like I drive to visit my brother in Tulsa and I find that my average speed was 65 miles per hour between here and Tulsa, then that means at some point during the trip I had to be driving exactly 65 miles per hour, right? There's no way I could make the whole trip driving less than 65. There's no way I can make the whole trip driving more than 65. And as I switch from less than to greater than, I I have to at least drive 65 miles per hour at one point. And that's what the mean value theorem is saying. So consider a fixed point iteration with some fixed point. This is a definition of the attracting fixed point. If I use the word attracting fixed point, this is exactly what I mean. X star is an attracting fixed point if there exists some interval, it could be big, it could be small, but there's at least some interval, with a radius delta. And delta, like I said, it could be big or it could be small, but it just has to be a positive number, greater than 0, not 0, such that every real number initial iterate inside that interval we're talking about generates a sequence that converges to the fixed point as, and this is another typo I'm going to have to fix later, n approaches infinity. Sometimes drawing a picture helps. Here's my real number line. And what I'm saying is, if I have a fixed point here, this would be an attracting fixed point if there is some interval with a radius delta around this fixed point where any starting iterate inside this interval eventually converges to the fixed point, right? That's what makes it attracting, is all the points near the attracting fixed point end up getting attracted to the attracting fixed point. And it doesn't have to be that way for the whole real number line, but it has to be that way for an interval of points near the attracting fixed point. So any initial iterate in this interval converges to the fixed point. That's what makes it attracting. Okay, so next is an important theorem. This theorem says a fixed point is an attracting fixed point if your function is well behaved. So in this case, your function is continuously differentiable. We can just assume that almost all the time, right? But your fixed point is an attracting fixed point if the derivative of your function at the fixed point has an absolute value less than 1. Then that means it's attracting. So how do we know that a derivative absolute value less than 1 means this is attracting? We would say my function f is nice and continuously differentiable along some open interval containing the fixed point, and assume that it's true. Assume that the derivative's absolute value is less than 1. Now, choose any number capital L such that whatever this is, since it's less than 1, I can always find a number, I can always find a real number in between that and the number 1. So if this is a value of like 0.9, well then my capital L could be a number like 0.95, for example, because it has to be less than 1 and greater than that. Since the derivative of f is continuous, then there exists some radius, some lowercase delta, some real number greater than 0, such that the absolute value of the derivative is less than or equal to L for all values x where the distance from x to the fixed point is less than the radius of the interval. So let me draw this picture again of my real number line. And then we've got some fixed point that we want to say is an attracting fixed point. And here, here is going to be a curve describing my f prime, my derivative. And let's say this is a value of the derivative equal to 1. So we've already decided that the value of this derivative is less than 1 here. Like maybe it's like 0.9. Well, it's a continuous function, so it can't immediately jump up and be greater than 1. It has to slowly, eventually cross this threshold where it becomes greater than 1. And that means inside this little interval, we can define a new interval where that's delta away from my fixed point. And whenever we're talking about this x, all x where the distance between x and the fixed point is less than delta, we're talking about all of the points that are like here, where the distance from the point to the fixed point is less than delta. There could also be a point here, where the distance from there to the fixed point is less than delta. And for these points, it's also true that their derivative is less than 1, like there is in the picture. And again, that's true because the derivative is continuous. So it can't jump around on us. It's got to remain connected. So now the mean value theorem implies that there has to be a point C between x star and any x in that interval. So the point C I'm talking about could be like here, between x star and x, such that this, right? This is the mean value theorem. That the instantaneous rate of change at some point is equal to the average rate of change of that function. And so we rearrange it a little bit. What happens in the next step? We multiply both sides by parentheses x minus x star. What happens in this step? We just take the absolute value of everything. And then in the next step, what we said prior to this is that there is always a point, if this is less than 1, we can always find a real number, capital L, that can squeeze in between. It doesn't matter how close that number is to 1. If we're dealing with the real numbers, we can always squeeze in another real number in between. So that's what the capital L is about. And if that's true, if this f prime of c absolute value is less than L, well, then I can swap it out with an L and change this equality to an inequality, since L is larger. Now, what happens when we iterate this? I'm not just going to take the function evaluated at some point and just be happy here. What I'm going to do is I'm going to take a function and evaluate it at that point, and then evaluate it again, and evaluate it again, and evaluate it again, because this is a fixed point iteration. That's what we're doing. We're doing multiple iterations of this to see where it converges. And having done it twice, having done 2 iterations, well, f of x star is just x star. That's what it means to be a fixed point. And then over here, we've got L times, well, previously it was x minus x star, but now it's going to be f of x minus x star on the second iteration. And that means using this here would get me L squared times the distance from x to x star. And the next logical step is, okay, like we've done it once, we've done it twice. What happens if I do it n times? Well, then I would end up with getting L to the n power. This equation right here is saying the distance between the nth iterate of x and the fixed point is going to be less than or equal to L to the n power times the distance from the initial iterate to the fixed point. And since that capital L is less than 0, L to the n power is going to approach 0. as n approaches infinity. Right, because even 0.999 would eventually approach 0 when you raise it to the millionth power, billionth power, trillionth power. And that means on the right-hand side, if this is approaching 0, and the left-hand side is less than that, approaching 0, there's like a sandwich theorem or something from Calculus 2 that says that sequence on the left-hand side also has to approach 0. So the distance between the nth iterate and the fixed point is going to approach 0 as n approaches infinity. That's the definition of attracting fixed point, right? That nearby points should eventually converge to the fixed point. And so that concludes the proof. So all we really need to test if a fixed point is attracting or not is take the derivative of the function at the fixed point, take the absolute value. Is it less than 1? Then it's an attracting fixed point, and it should have a basin of attraction. It should have a kind of interval where all of the points nearby are going to converge to it. Okay, next definition. Same thing exactly, but with very few changes. This time I'm talking about repelling fixed points. So if you have a fixed point iteration and some fixed point, then that fixed point is going to be a repelling fixed point if there exists some interval with a non-zero radius around that fixed point such that any initial iterate in that interval is going to generate a sequence that does not converge to the fixed point. It might diverge, it might enter a cycle, it might do something, but whatever happens, the initial iterates inside that interval are eventually going to leave that interval. They're not going to stay there. I can tell right away if a fixed point is a repelling fixed point because I'll take the derivative and then take the absolute value of that function at the fixed point. And if it's greater than 1, that tells me it's repelling. Just like less than 1 means it's attracting, greater than 1 means it's repelling. If it's equal to 1, then it's inconclusive, right? We don't really know yet if it's attracting or repelling if you get a derivative equal to 1. You have to do a lot more investigation there. So the proof is also going to look exactly the same since the definitions are pretty much the same. The proof goes like this. Suppose f is a continuously differentiable function. Assume that the derivative at the fixed point is greater than 1. And if the derivative at the fixed point is greater than 1, then I can always sneak in a real number L that's greater than 1 but less than that derivative. So it's right there in between. Since f prime is continuous, there would exist some radius delta such that, like I said, this is the point 1. This is my real number line. And here's my fixed point. And here is my f prime function. F prime has to be, greater than 1. Almost started drawing the same picture, but it should be greater than 1 here at the fixed point. And there's going to be some interval where that's true. Draw that interval here. Where the radius of this interval might be like delta. And then we might have some other points here that belong to the interval, so that the distance between the fixed point and the new point x is less than delta. And then we can always sneak in some real value c in between there. That's the picture you should remember. But the idea is, since the f prime function is continuous, and I know that f prime of x star has an absolute value greater than 1, then there also has to be points around it where the absolute value of f prime is greater than 1. So again, use the mean value theorem. And mean value theorem says, this point C has to exist where it satisfies the mean value theorem from the x to the x star. And multiply both sides times parentheses x minus x star, put absolute value around all the factors, then we're going to swap out this with a capital L because we said earlier that f prime of c, absolute value, is going to be greater than 1. And if that's greater than 1, then I can always sneak in a little number in between 1 and that value. And if this equation is true, the left side is equal to the right side, and the right side is greater than this L times the absolute value, then the left side should be greater than or equal to L times the absolute value. And then once again, we're going to iterate this, which means I don't care just what happens with one application of the f function, but I care what happens with 2 and with 3 and 4 and 5 and n applications of that function. And on the right-hand side of the inequality, we're going to end up with capital L to the n power. And since L is greater than 1, that means L to the n power is going to approach infinity as n approaches infinity. So the right side of the inequality is growing, and that means the left side of the inequality also has to be growing. The left side of that inequality is the distance between the nth iterate and the fixed point. So the distance is growing every time we iterate, at least until the iterate leaves this interval where all my arguments are valid, right? At least until it leaves the radius delta. Once that initial iterate gets outside of this interval, then we don't know what happens after that. But the main point is that it didn't converge to the fixed point. It left the neighborhood. Okay? And that's what it means to be repelling. So I can have a fixed point if the input of the function is equal to the output of the function. It's attracting if the absolute value of the first derivative is less than 1. It's repelling if the absolute value of the first derivative is greater than 1. And if I've ever used the word basin of attraction, this is what I mean by basin of attraction. For an attracting fixed point, its basin of attraction is the largest connected interval containing the fixed point, for which every point in this interval is going to converge under iteration to the fixed point. So here's my real number line. Here's my fixed point. Let's say this is my basin of attraction. So anytime I start inside this basin of attraction, iterations are going to eventually converge to the fixed point. But if I were to start outside of the basin of attraction, then iterations are going to move away from the fixed point or enter a cycle or do something else. They're going to have some other kind of behavior. Oops. So one thing you might be interested in as a mathematician is, how do I find a guaranteed basin of attraction? How can I guarantee that my fixed point iteration is going to converge? Well, we're going to find the largest connected interval, we'll call it A to B, that contains my fixed point, for which every point in this interval is going to have an absolute value of first derivative of f less than 1. That's the trickiest part. The next is, we say this lowercase delta radius is going to be the minimum of the distance from the fixed point to A and the fixed point to B. So I have this interval, let's say, from A to B, and it's not necessarily symmetric. Okay, this guaranteed, sorry, I'm not even talking about the guaranteed basin of attraction right now. I'm talking about this. This interval from A to B is not necessarily symmetric. It might happen that A is a lot closer to the fixed point than B. It might even happen that B is infinity. Or maybe b exists, but a is negative infinity. Or maybe a is negative infinity and b is positive infinity. But it's not necessarily symmetric. They don't have to be the same distance. So what we'll do is we'll let delta be the smaller of the two distances. The smaller distance from the fixed point to an endpoint. And then the guaranteed basin of attraction is going to be smaller than that. The guaranteed basin of attraction in this case, with my picture, would be only from here to here. Because this distance would be my delta, and this distance would also be delta. So a few important things to note is that just because the absolute value of the derivative is less than 1 does not mean that it's going to converge to your fixed point. Because these points here that are in between my yellow bracket and my purple bracket where b is, all of these points, they might actually diverge away. Right? It's not part of the guaranteed basin of attraction. The other thing to notice is that like the guaranteed basin of attraction is not always the entire basin of attraction, because sometimes you could have points like right here that are in the basin of attraction, but they don't somehow fall into the guaranteed basin of attraction. It's just some things we can never know, you know? So that's why I typed right here. It's important to distinguish between the actual and the basin of attraction and the part that we can guarantee. The actual basin of attraction may be larger. Let's actually do one. So exercise 5 says determine the guaranteed basin of attraction for the following fixed point iteration. So step 1 says we're going to find a fixed point. And my fixed point is going to be something like this. And R was the Reynolds number from last time. If you remember the Reynolds number, it was like rho v d over mu. We don't have to use exactly the same number that we used last time. Remember, the viscosity was a pretty small number. The density was about 1,000. The diameter was like 0.1 from last time. The velocity was like 1. And so altogether, the Reynolds number was a big number. It was like 100,000-ish. I'm trying to remember what we did last time, but that was kind of what it was. So let's try to find this again. And so I've got the left-hand side and the right-hand side of my equation. We've got to choose some initial iterate. I might as well choose the number 1, I guess. And then for the right-hand side, it's going to be like 1.93 times log base 10 of r, whatever I want my Reynolds number to be, divided by x minus 0.537. And then to get my new left-hand side, we just set it equal to the right-hand side, and I can just fill down these formulas and see what happens. Oh yeah, I always forget this. I have to lock in the cell reference for the Reynolds number. There we go. So there's my fixed point iteration that we had last time, and again, it's converging to something. It's converging to 7.43. And so I know that my basin of attraction has to include that fixed point. Now, let's take the derivative and evaluate the derivative at the fixed point. And so this fixed point iteration is like something like this. Let's call this function g. So g of x would be equal to 1.93 times log base 10 of 100,000 divided by x minus 0.537. And we're taking the derivative. When I see log base 10 of 100,000 divided by x, can somebody tell me how to simplify that using a property of logarithms?
Log 10 to 100,000 minus log 10x.
Perfect. Yeah, if I'm dividing on the inside of a logarithm, I can subtract and make it two logarithms. And so what is log base 10 of 100,000?
The derivative of it is 0.
That's true. So I don't even really care. But now I'm curious, how many zeros do I see? 5, right? So that's 10 to the 5th power. And so it's 5. But you're right. The derivative of a constant is 0. So now I've got negative 1.93 log base 10 of x minus 0.537. And what I want to do, oh, sorry, I didn't take the derivative yet. What is actually the derivative of this? It's going to be 1 over natural log of 10 times x, I believe. Right, okay. Not to try to teach a whole calculus 1 lesson here, but the logarithm base 10 of x is the same thing as the natural log of x divided by the natural log of 10. And so that's why you end up with the natural log 10 here after I take the derivative. Okay, sorry. Now I've got the minus sign. And now I have the proper derivative, which is 1 over natural log of 10 times x. And then in the derivative, I don't have a constant anymore. That constant should go away. So there we go. Much better. And the question is, what happens if I plug in my fixed point, which is like 7.43? Is this derivative going to be, is it going to have an absolute value that's greater than 1 or less than 1? It's going to be negative 1.93 divided by natural log of 10 divided by 7.43, right? So it should be negative 0.113. The negative doesn't matter so much because we're about to take the absolute value anyways. But I do care that's 0.113-ish. Because the absolute value then is less than 1. So this is an attracting fixed point. We kind of already knew that it was attracting just because it works as an iterative technique and it's converged to that point. Otherwise, if this was a repelling fixed point, it wouldn't work. You'd never be able to find it. with the fixed point iteration if it was repelling. So we already knew that, okay? But now, my next step in this whole process is to say, I need a new piece of paper. And then with my new sheet of paper, we say, what is the interval from A to B for which x in A to B implies that the absolute value of the derivative of this iteration at x is less than 1. And g prime of x is negative 1.93 times 1 over natural log 10 times x. Yeah, okay. Now I don't care that it's negative, because I'm about to take the absolute value anyways. And 1.93 is a positive number. Natural log of 10 is a positive number. The x, we're not so sure about. But I could write something like this. Just by multiplying both sides times absolute value of x. And this tells me that the absolute value of x has to be greater than 1.93 divided by natural log of 10. 1.93 divided by natural log of 10 is 0.838. And this is telling me, the equation is telling me that the absolute value of x has to be greater than 0.838. I don't care about the negative values of x. I don't care about the negative values of x because in my fixed point iteration, if I had a negative value of x and a positive Reynolds number, then I'm taking the logarithm of a negative number, and I don't care about that, right? I only care about positive values of x. Otherwise, it doesn't apply to my fixed point iteration. So the positive values of x that I care about are greater than 0.838. And so whenever I talk about what is my interval from A to B, my interval is the interval from 0.838 to infinity. All of those values have this property that g prime of any of those numbers is going to have an absolute value less than 1. So which one is closer to my fixed point, A or B? Obviously, 0.838 is closer to 7.43 than infinity. And so I'm going to calculate that delta radius as being 7.43 minus 0.84 or 838. I don't know. I'm keeping 2 digits after the decimal, so I'll just make it 84. And then that's 6 point something. .69. And so that is the radius of my guaranteed basin of attraction. That's around the point 7.43, that fixed point. And so my guaranteed basin of attraction is going to be the interval from 0.84 up to 7.43 plus 6.69, which is going to be 14.12. Do you see how I got that? It's the fixed point minus the radius and the fixed point plus the radius for the guaranteed basin of attraction. Where my fixed point is about 7.43, yeah. So a few things to notice. This is not my guaranteed basin of attraction. This is just the interval where g prime of x has an absolute value less than 1. But there are going to be numbers between 14 and infinity that don't converge, okay? So this is not the basin of attraction. This is the guaranteed basin of attraction, but it's not necessarily the whole basin of attraction. In fact, there might be numbers less than 0.84, and there might be numbers greater than 14.12 that don't converge either. Or sorry, that do converge. I misspoke. There might be numbers greater than 14 that do still converge, even though they're not inside the guaranteed basin of attraction. And so really the only way to figure out your actual basin of attraction is just to try a whole bunch of different starting iterates and see if they converge, kind of like we did on Wired Wednesday. Remember our Wired Wednesday with our pretty fractal pictures? That's really the only way to actually see what your basins of attraction are, is if you just try a whole bunch of different starting iterates around there. All right, so let's try some things. What if my starting iterate is less than 0.84? Like what if it's 0.82? Okay, that still converges. Even though I'm outside my guaranteed basin, this still converges for 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, about 0.01. Yeah, it still converges even outside the guaranteed basin. Okay, the upper limit was 14, so that should converge. What about 15? It still converges. 16, 17, 18. What about 1,000? Still works. What about 10,000? Still works. What about 100,000? Or yeah, that's 100,000. Okay, so it breaks around 100,000, and it doesn't converge anymore after that. And like I said, not all numbers up to infinity were going to converge, but also a lot of numbers that were outside of that guaranteed basin still converge. So, you know, a lot of times in math theory, there's only so much you can really know. Only so much you can guarantee, but that's how it works. All right, exercise 6 says determine the guaranteed basin of attraction for the following fixed point iteration. And when I say following fixed point iteration, this is what I'm talking about. It's Newton's method, or fixed point iteration Newton's method. And I've already typed out the solution, so we can just talk about it. One of the things I need to do is I need to take the derivative of my function f, which is my Newton map in this case. And in this step, when I take the derivative, I'm thinking about the derivative quotient rule. Okay, so you take the derivative of this using the derivative quotient rule, and we're going to simplify because g prime squared divided by g prime squared is just 1. 1 minus 1 goes away and it's just a 0. And then I see a negative here and a negative here, and that makes a positive. And so that's why this simplifies to be just g times g double prime divided by g prime squared. And the rule for finding my guaranteed basin of attraction is to say we need f prime absolute value to be less than 1. So we set that less than 1 and multiply both sides times g prime squared. And so that's a nice little rule to remember. If you're using Newton's method to locate a root of g, then let me say this. If I want to know what is f prime at the root, this is 0, right? And 0 times anything is 0. As long as g prime is not 0, then that's obviously true. So as long as we're using Newton's method to locate a root, then every root of my function g is an attracting fixed point because the absolute value of f prime is less than 1. 0 is less than 1. And that's true whenever the derivative g prime is not equal to 0. It may still be the case that when the derivative g prime is equal to 0, that it's an attracting fixed point. But in this case, you'd have a 0 over 0. It would be indeterminate. You wouldn't really know. To find the guaranteed basin of attraction, we solve the following equation for x. And it's just the same one from before. You're trying to find the edges of the interval, right? You're trying to find like the a and the b, where this goes from being true to not true. So you set this equal to each other. And then you can find the possible a and b. And you're not done. That's not the guaranteed basin of attraction, but you find which one's closer to your fixed point, which one's closer to the root. And then you take the radius as being the minimum distance, the smaller of the two distances, and then you make that interval symmetric around your root. Okay, one more little problem in my notes and we'll be done for today. It says, find the guaranteed basin of attraction for the Newton map of sine around the 0 at 0, because we know that sine of 0 is 0. Okay. So my Newton map is going to be x minus sine of x divided by what? Cosine. Because it's the function divided by its derivative in the Newton method formula. So we want to know, when is f prime going to have an absolute value less than 1? That's what we're trying to find here. So let's take the derivative. And in fact, we've already done a lot of this work. We've already done this to the point where we know we have to find this. The function times its second derivative equals, the function times its second derivative equals the first derivative squared. That's what we found in the previous problem was true for all Newton maps. These will have solutions a and b for that equation. But in any case, the g function is going to be sine of x. The second derivative of sine is negative sine. And then the first derivative of sine is cosine. So we get something like that. Only I think I forgot absolute values, didn't I? Yes, those are supposed to have absolute values. So that is what we're solving. Okay, so if it's absolute value, I don't care about the negative. This is just sine squared x equals cosine squared x. And that's clearly true whenever sine is equal to cosine, or at least absolute value of sine is equal to absolute value of cosine. And so think about this. If my fixed point is 0, not because sine of 0 is 0, but because that's a 0 of my function, and the Newton map is going to have an attracting fixed point at the zeros of my function. If the fixed point is equal to 0, then I'm looking for solutions of this equation in order to find my a and my b that are near 0. So what are solutions to this equation near 0? When is sine equal to cosine? Or when is negative sine equal to cosine?
Pi over 4.
Yeah. At pi over 4, sine is equal to cosine, because they're both equal to square root 2 over 2. So that would be larger than my fixed point, right? What's a number that's less than my fixed point? What's a number that's less than 0 for which the absolute value of sine is equal to the absolute value of cosine?
Negative 3 pi over 4.
Perfect. Negative pi over 4. So there's an interval from negative pi over 4 to positive pi over 4 where the derivative of the Newton map has an absolute value less than 1. Okay. And this time they're actually equidistant from my fixed point. So I don't have to find the one that has a minimum distance from my fixed point just because it's symmetric already. And so this is my guaranteed basin of attraction. So the guaranteed basin of attraction is from negative pi over 4 to positive pi over 4. If I start my initial iterate of Newton's method in between negative pi over 4 and positive pi over 4, then I expect my Newton method iterations to converge to 0 when it finds a root of the sine function. I probably have a good Desmos thing to look at.
It's negative 3 pi over 4, not negative pi over 4.
So you're right that like sine is equal to cosine at negative 3 pi over 4 because they're both negative square root 2 over 2. But I don't need sine to be equal to cosine. I just need the absolute value of sine to be equal to the absolute value of cosine. Yeah. Yep. So let's see if I can find my Desmos thing. Oh my gosh, you're joking me. Oh, it's because this is Edge. I need Chrome for it to work. Now we try. Okay. Where is numerical? Newton's method. My function is going to be sine. Okay. So let me put in x equals pi over 4. That's my upper bound. And x equals negative pi over 4. That's my lower bound. And what I'm saying is if I start my initial iter anywhere between these upper bound and lower bound, it should always converge to the root at 0. If I go too far away, well, then maybe it doesn't converge to the root at 0. Like this one, even though I start my initial iter at 1.3 or so, the iterations of Newton's method bounce off here and end up converging to the negative pi 0 of sine. But again, this guaranteed basin of attraction doesn't necessarily include the entire basin of attraction, because that is still a point that we would say belongs to the basin of attraction because it eventually converges to my attracting fixed point, but it's not inside the guaranteed basin. And that's kind of a disappointing thing, that you don't get the whole picture. You just get some kind of guarantee. Yeah, sine is interesting because sine can kind of do some kind of crazy things.